Welcome back, ladies and gentlemen. Today is section 11.7. It's all about geometric probability today. Up on the screen, you'll see your exit question for the day. The first thing we're going to start off with is a definition for probability in general. And then what we're going to do is we're going to take what we know about area and we're going to calculate the probability that something will occur in a certain area, length, or even sometimes a volume of a given region. So first we need to know what probability is. You probably have a very good understanding of this already. I'm just going to introduce you to the very formal definition and the formula to calculate probability. Simply stated, a probability is a ratio expressing how likely it is that an event will occur. Its definition slash formula is a fraction. It is the number of favorable outcomes divided by the number of total outcomes. So an outcome is the outcome of an event, whether it happened or whether it didn't. And you have to be able to count these things accurately. So how many ways are there to get something that you're measuring, and how many ways are there to get something at all, total? What is the total number of possibilities? The other thing that I'll mention about this definition is that it has a very misleading word in it, and that is the favorable outcomes. Favorable doesn't mean, in this definition, favorable does not mean that it is likely to happen. It could have a very, very small chance of happening. What favorable means is that you're measuring it. So it's the outcome that you are interested in. So if we were flipping a coin and we were trying to figure out what is the probability that we're going to get a heads, the favorable outcome would be getting a heads to turn up. Now, in that case, it's a 50-50 shot, and it's pretty likely that a heads will happen. So maybe think of putting all the numbers 1 through 100 in a hat and drawing out 1. The likelihood that you're going to draw 1 out of all of the numbers is very, very low, but we would still call that the favorable outcome because that's the one that we're trying to measure. Next up, we got a little bit of notation which may or may not be new to you. First, we have a vocab word event. An event is something that can be measured as happening or not happening. So the only real restriction on what an event is when we deal with probability is that it has to be measurable. It can't happen and not happen, and it can't not happen either. So it has to be measurable whether it has happened or not. That's pretty much the only restriction of what an event can be. So I have a very simple example here where someone has rolled a die, and you see the 6 different outcomes there in the picture. And we have 4 events defined. Event A is that a 3 is rolled. Event B is that a prime number is rolled. Event C is that any number is rolled. And event D is that a 7 is rolled. If you wanted to go ahead and go through and calculate all the probabilities for this, we would count how many ways is there to roll a 3. Well, there's just 1 and 1 out of 6. Then we go on to what is the probability that a prime is rolled. That would be 2, 3, and 5. So there are 3 out of 6 possible ways, and then reduce that to a half. And then a number is rolled. Well, every single time I roll a die, I should come up with a number unless by some weird freak coincidence it lands on its edge or a corner somehow. An event D is that a 7 is rolled, and there's no 7 there, so that should be a 0. So event C should happen all the time, so 6 out of 6 times. And event D should happen 0 out of 6 times and should have a probability of 0. So that brings me to some new notation for you that you may or may not know. This says the probability of A happening is 1/6. The probability of B happening is 1/2. And then, of course, these events are defined somewhere else in the context of the problem. So you can shorten up the sentences or the descriptions that you need to write using this notation very, very easily. The one thing I do want to just draw your attention to real quick is that all probabilities are a value between 0 and 1. So if you get a negative value for a probability or a probability that has a value larger than 1, then you know you've made some sort of mistake somehow. You've miscounted or miscalculated something. The other thing is that I will totally accept a probability in terms of a fraction, decimal, or a percent. So if you like working in percents and those make more sense to you, go right on ahead. Uh, I'll just deal with your answer as you give it to me in some form. Geometric probability. This is a new concept for you, which is simply a probability ratio involving a measure of length, area, or even volume. And generally when we do a problem that has to do with geometric probability, we assume that every point within the given region that's defined has an equal chance of being chosen. So if we talk about this board here, it is just as likely to land in any particular spot as another. And that's the basic assumption. From there, we need to be able to calculate the size of all these sectors and all that to figure out what the probability is of landing in one of these colored regions. So that means that we have a couple key concepts. These are not theorems. So don't look for them on your theorem sheet. These are just key concepts. Probability and length. The probability of choosing a random number on a number line. So the probability of the length of CD divided by the length of AB. So what is the probability that I would pick something or something would land in this segment of the line? Would just simply be the length of CD divided by the length of AB. Likewise, you can do the same thing with area, and again, volume. We're not going to talk about volume today, but you basically just find the area of the favorable outcome, the outcome or the region that you're interested in, and then divide it by the total area that the event has to happen in somewhere. So, first question, find the probability that a point is chosen at random on PQ, and knowing that PQ is on RS, or sorry, a point chosen at random on PQ is also on RS. So the probability that the point is on RS and PQ, given that it's on PQ, what is the probability that it's on RS? Well, you just need to know the lengths of the two segments. So the total length, PQ, is 10 units. The smaller segment, the partial segment, is 6 units long. So you simply divide the two with the RS being on top because that's what we're trying to measure. How likely would it be that it's in that segment? And then of course reduce. So 6/10 goes down to 3/5. And I chose to define the event as event A. Next one. What is the probability of a dart hitting the pink area given that the dart will hit the board somewhere? Well, we have to split this problem into a little bit more manageable chunks. The probability of this event happening, I'll call it event A, is the probability that the dart will hit somewhere on this ring, or the area of this ring divided by the area of the whole board. So we need to find the area of the whole thing, subtract the inner circle to get the ring, and then once we do that, we'll have all three areas that are involved here. So the whole area is pi r squared. The inner area is pi r squared again, just with two different radii. And if you go ahead and calculate that, you do a little calculation, and then these are like terms, so you can combine them into 21 pi. So the ring, the area of the ring is 21 pi square units. Then moving on to the probability calculation, we're going to take the area of the ring divided by the area of the whole board, which we had already previously calculated. And these are both in square units, but when you divide them, the units cancel. So technically I should have had a unit squared down there, but I no longer need the unit squared right here because if I had meters over meters or meters squared over meters squared, in this case centimeters squared over centimeters squared, the centimeters squared, the units themselves actually cancel each other out, as do the pi's. So the final probability of landing somewhere in the pink region here is 21 over 5, and then you could, of course, convert that to a percent if you wanted to. There's your assignment. I'll see you next time.